engineer at Google. I'm also the tech lead of the O3D team, and I'm going to be giving this presentation today with Gregg Tavares, who's lead engineer on the project as well, and sort of an API guru. But I was wondering before we start, if I could get with a show of hands, how many of you have actually downloaded and sort of looked around O3D? Okay, there's a few people. Can I ask you how many of you have actually done any graphics programming with stuff like D3D or OpenGL? All right, a lot more. Excellent. All right, cool. So we kind of figured that it would be a pretty diverse audience. So what we did is we split the presentation in two parts, really. So I'm going to start with an overview of O3D. I'm going to give you sort of a high-level view of what the API is and what the goals were in designing that API, and focus on a few different sort of areas that we think were sort of unique about O3D. And in the second part, Gregg will take over and will actually show you how, in about 20 minutes, you can make a little game application. So that should be fun, and hopefully it'll be good for you guys too. So O3D. O3D, as you probably know, is a JavaScript API for doing GPU-accelerated graphics inside a web page. Right now, O3D is a plugin for... Oh, was I talking without slides? Okay. O3D is a plugin for all major browsers, including IE, by the way. And runs in all major operating systems. Right now, like I said, it's a plugin, but we're hoping that will be integrated more closely inside the browser, starting with Chromium first. What kind of applications you can run with O3D? It's really entirely up to you guys. If you go to our website, you're going to see a few samples of applications, things that we thought were sort of interesting to do in 3D. The obvious ones are games. Data visualization is another type, the sort of the type of, Google Earth displaying data on a map, stuff like that. Other sort of 3D scenes and modeling sort of tools, and tools that allow you to sort of spin around 3D models. These are obvious examples. But in reality, any application that you can currently do natively with 3D graphics, you can probably do with O3D and run it inside your browser. Before we go into details of the API, I think it would be a good idea to sort of tell you a little bit about the goals that we had when we were designing the API. The first goal is we wanted something that's really expressive. So we were really we wanted, the idea behind O3D was it needed to be an API that would be capable of doing sort of complex rendering. And if you think of complex rendering, 3D rendering, your mind typically goes into video games. So video games are sort of probably the most complex 3D apps that you find today. So we wanted to design an API that's capable of handling that level of complexity. We wanted something that you can create really sort of complex rendering worlds, multi-pass effects, doing reflections, nice shaders in your objects, stuff like that. We know that we're running inside the browser, so performance is a major concern, was a major concern for us. So we took several steps to make sure that our API is really performant for cases where you have really large scenes with a lot of objects, which are typically hard to do in an environment like the browser. The second goal that we had was we want to make an API that's really flexible. We really didn't want to make any assumptions that we're making an API specifically for making games or for making other types of applications. We really wanted a fairly low-level API that would allow you to do pretty much anything you wanted to do with 3D graphics in the browser. And finally, we're really big believers in the one web idea. We wanted really the applications that you write to be able to run exactly the same way, if possible, on all browsers or operating systems. This is both for the benefit of the developer, so you as a developer can just sit down on your machine and write an application and sort of be sure that it's going to run on everybody else's machine and they're going to have the same experience as you're having when you're looking at it. But also from the user's perspective, in that when you go to a website that has O3D content, you want to be sure that it actually works. The way we did that is we sort of decided early on a spec of graphics hardware that we decided to support, and we said whatever is capable of running on that hardware is good and is going to run GPU accelerated. Everything below that, we have a fallback plan, which is going to be run it in a software renderer. But regardless of the case, you're actually going to see the same images rendering in your browser. Having said that, this is a list of a few of the sort of feature highlights. Obviously, the API is fairly big, and there's a lot of other features, but these are features that are important to remember. First of all, like I said, we wanted to provide a very flexible API, so we really give you fairly low-level access to the graphics hardware. So we allow you to write your own shader programs using HLSL and CG as the shading language, which gives you really full access to modern graphics hardware. We also have the API in such a way that you can do modern rendering effects, like multipass rendering. For example, you can render an entire scene into an off-screen buffer and then take that buffer and use it for something else, and this allows you to do more complex effects, like if you wanted to do motion blurs, depth of field effects, stuff like that. So this is all possible with the API. We give you full control over the render state, so you have very fine-grained control over how you do blending, things like that. We also expose image loaders beyond what the browser actually supports, so we load a few compressed formats that support levels of detail as well. You can load them directly in O3D. Another thing that we've implemented within O3D, which is sort of escapes a little bit from the typical rendering side of things, is we added a fairly low-level animation and skinning system, which would allow you to do animated characters within your application fairly easily. You can author them somewhere else and have them exported and have them running in O3D with very little effort. And this is something that we wanted to do natively inside the actual plugin, because we thought, and we still believe, that JavaScript is probably still not fast enough to do some of these things that are necessary, some of the calculations that are necessary for that. We know that different browsers have different performance in terms of JavaScript. So while JavaScript is generally getting faster in all browsers, there's still a big disconnect between various browser implementations. And we realized that fairly early on. So what we ended up doing is we actually embedded Chrome's V8 engine, which is one of the fastest JavaScript engines around, within the O3D plugin, which means that you can select whether you want to run your code inside the embedded V8 engine, so you're going to get the same performance on the same PC regardless of the browser you're running, or whether you want to run it inside the browser's JavaScript engine. So you have this option to do. And finally, we also opened an API that allows you to import assets, 3D assets, in the browser that's based on JSON. I'm going to say a little bit more about that pretty soon. So really quickly, just to give you an idea about APIs, typically graphics APIs fall into one of the two categories. There's the immediate mode APIs, in which graphics commands are executed sort of immediately as you enter them. And the side effect of immediate mode APIs is that if you have a frame and you want to sort of change something inside the frame, you really need to redraw the entire frame, so you need to draw everything that's in the frame. Typical examples of immediate mode APIs are, the Direct3D and OpenGL, which are the low-level APIs that are used for rendering natively. But also, if you think in the HTML world, the Canvas 2D surface is an immediate mode API. On the other side of the spectrum, you have retain mode APIs, where instead of actually issuing the draw commands one after the other, you actually describe first the objects that you want to render. There's typically some sort of a singgraph structure that's associated there. And then the high-level information is retained between frames, which means that the actual system can redraw your frames without you having to execute code, other than the code that you need in order to sort of make whatever changes you need to make from one frame to the next. And typical examples of that are, most game engines fall in the retain mode API category. In the HTML world, SVG is a retain mode API, and the entire sort of HTML DOM, you can think of it as a retain mode API, where you describe the page contents first, and the browser knows how to render the entire page. And to make this a little bit more concrete, imagine you had this example where you had a very simple scene. You had a red sphere that you wanted to move to the right over time, and a green square that stays constant. If you were to use immediate mode, what you would have to do mostly is, in every frame, you would have to execute commands to draw everything, the contents of the entire scene. So you have to clear it, move your cursor to a position, set your color, draw the circle, then move to a different position, set a new color to green, draw a square, and repeat that process for every frame. Now, if you look at the retain mode API, the process is a little simpler. So a lot of the code actually moves to the initialization step, in which you create some higher level constructs where you say, I have a circle that's red and a square that's green. I know that the square is not going to move anywhere, so I'm going to set it in a specific position. And then all you have to do each frame is actually move the circle, set a new position of the circle, and and repeat that, and the actual system will be able to redraw itself. Why this is important, the difference between these two approaches, is that the stuff that you see in the green box is actually stuff that would be running in JavaScript. So if you were running at a really fast frame rate, say 60 frames a second, which is sort of a common frame rate for interactive application, you have 16 milliseconds to issue all these draw calls. Imagine a scene that has hundreds and hundreds of objects. It's going to be hard to actually execute all that code and still have time to do your application logic. So in some cases, retain mode API is advantageous in terms of performance. So where does O3D fall in? O3D is really a low-level retain mode API. That's the way we want to think of it. It has a lot of the flexibility of immediate mode API, but a lot of the performance-critical aspects of rendering, like Z-sorting for getting the transparency, so the transparency correcting, doing culling, animation, all that, are executed in native code. And if you look at the spectrum of APIs, you look on the far left, there's OpenGL and D3D, which is definitely sort of the lowest level API that you'll see. O3D really falls very close to that, as opposed to the other end of the spectrum where you have the game engines that are super high level. And sort of somewhere in the middle, but more towards the right side, is the full-fledged scene graphs, like stuff that you see, like, say, the Ogre API, stuff like that. That definitely have a lot more sort of higher level features, that collision detection, potentially physics, stuff like that. O3D is definitely a lot more low level. Stuff that you see in O3D, like I mentioned before, typically retain mode API has some sort of hierarchy. You're going to see in O3D two types of graphs. You're going to see the transform graph, which is sort of a typical graph that you see in scene graphs, where you have a bunch of transforms that describe where your objects get rendered, and also the shapes, which are the actual meshes that get rendered. The shapes in our world, because we are fully shader-based, they get associated with materials and effects that contain the shader code. But this is a pretty common structure that you see in scene graph APIs. What is a bit novel about O3D is a different type of graph that we have, which is called a render graph. And the render graph is really the recipe for drawing 3D objects. Like I said before, we wanted to allow more complicated effect, like doing multi-pass rendering, stuff like that. In order to describe that kind of rendering, we needed a different data structure from the data structure that actually holds the objects. And if you look at this is just an example of a typical render graph that does both transparent and opaque pass. But typically what O3D will do is we'll parse this, we'll traverse this graph from sort of top to bottom, left to right, and we'll issue rendering commands based on the nodes. I'm not going to go into detail about what really happens in there, but I thought I'll give you an idea of what you'll find in a render graph, because Gregg is going to mention render graphs a little bit later on in his part. So as far as the experience with programming with O3D, the actual API is a fairly low-level 3D graphics API. So you'll definitely do a lot better programming with O3D if you had some experience with 3D graphics APIs like OpenGL and Direct3D. In order to make things a little simpler for those of you who don't necessarily have that experience, we've provided a fairly comprehensive set of JavaScript utility libraries that do certain things a lot easier. So with a single call, you can create common primitives like cube spheres, cylinders like that. You can create simple particle effects. You can create shaders. You can load. You can stream in files with assets, things like that. The utilities are not really part of the API, but they're there to make your job easier, and also they serve as very good sort of sample code, so you can use them, you can change them to fit your needs if they don't fit your needs. Finally, we expect that over time, there's going to be higher level libraries that will be developed on top of all that will make the tasks of writing O3D applications a lot easier for more developers, actually. So having said all that, an O3D application typically breaks down to two things. There's the code, which is sort of sets up all the rendering. It contains sort of the application logic, and you see a lot of code in the second part of this presentation. And then there's the asset part, which is really all the 3D assets that you need in order to render, texture, shaders, animation, stuff like that. And while we're on this topic, I thought I'd say something about assets. So with O3D, we decided to not invent yet another file format. There's tons of file formats for 3D stuff. Unfortunately, none of them really we thought was a particularly good fit for O3D. So what we did is we decided not to create yet another format, because at this point, like I said, we wanted this framework to be very flexible in the sense that we don't really know what kind of application you're creating. So we don't want to create a file format that sort of describes something that we don't know about. But what we did is we created an API that allows you to load in the browser these zipped archive files. And these zipped archive files can contain, generally 3 different types of files. They can contain text files, they can contain image files, and binary objects, binary buffer files. A typical application, for example, if you have sort of a general sort of rendering task that you wanted to bring in a whole scene, you would probably describe the contents of a scene in JSON format and store that in a text file. You would put all your textures in image files inside the same archive. And finally, all the heavy data, like, for example, vertex buffers, index buffers, animation, all that will go into binary buffers. So once you zip all that, and that's a process that you do offline, the application requests that file from the server sends it and streams it actually in, and then the application can extract the data from the file and can then start calling the regular O3D calls in order to actually create the objects. And this is we found that this is a fairly flexible approach to transferring any kind of data you want. But having said that, this is a bit abstract. In reality, a lot of the 3D applications really, require, general models with textures and all that. And in order to give you a leg up in that process, we decided to write really a sample, which is a converter that takes a Collada file, which is an XML representation of a 3D world. Collada files can be exported from most of the DCC tools today, like Maya, Max, even Google SketchUp. So you use the exporter from the DCC tool in order to create a Collada file. Then you use the O3D conversion. Okay? Cool. Hello? Okay, cool. So we have a tool that ships with the O3D SDK that really is a converter that takes a Collada file and zips, converts all the contents to this zipped archive format that I talked about right before. And then at the same time, we have a sample library, a JavaScript library that is able to load this file and create the O3D content that you have. So if you look into the O3D SDK, you're gonna find this tool, and actually in Gregg's part, which is about to start right now, he's gonna be making use of this to load content in the application.
Higher? Hello? Testing? Okay. So we're going to go over making an O3D application. This is just kind of a small sample start of a game. It's not like a really full game. But we'll go over all the steps, and hopefully a few days after the show, we'll be able to put them online. There's a few things that I have to fix, but they are here live. So the first thing you have to do is, like I said, O3D runs in a web page, so you need to set up a web page. So normally you would have a few script tags. In our case, we have our sample library. We include this script called base.js, and that kind of gives us an include facility for including other modules. And you can say here where we're requiring the module util and the module math. Then you have your body, and you see we have the onload set to call an init function. And then, because it's a plugin, normally it would run as an object tag, but object tags are kind of iffy in the sense that different browsers implement them in different ways. So you can still do that if you want, but our utility library instead looks for divs that have an ID that starts with O3D, and it will insert inside that div an object tag, and it will scale to the size that that div happens to be. So if we look at the next code, here's the init function that onload was going to call. And it's going to call this utility function called makeClients. It's an asynchronous function that, again, has to do with being cross-browser. Certain browsers don't necessarily create the objects the moment you ask for them. You have to keep polling until they actually have created them. So when it's finally figured out that it's created those objects, then it will call the function that you passed there, in this case, init step 2. And in step 2, gets past the list of all the objects that got created. In this case, we only created one, so we know we're just going to pull that out of that array. And then we pull out some globals here. The math is our math library. That's just to make our typing shorter. The client is the base object, the object that all the APIs start from. Then we create this thing called a pack. A pack is something that manages the lifetime of objects, and it's kind of hard to go into details, but the basic way to describe it is that all objects are reference counted, and the pack holds one count. So if you remove something in the pack, it loses that count. If nothing else is referencing, it'll finally get deleted. The next thing we're going to do is we're going to create a transform for the transform graph, and this is going to be our root transform. So everything from that and below is going to get rendered. And then we're going to call this utility function that will set up a render graph, basically the render graph you saw on the slide a few moments ago. Of course, you could create it by hand, but it turns out that for the most of the cases we've come up, this one routine will create a render graph that handles most of our cases. It passes back this object called that we store in this function called, or this variable called gViewInfo that we'll reference later. And you can see here we're passing in groot, which says this is the part we want to render, and the bottom where it says gclient render graph root is just attaching it to the client's root so that it will actually traverse this render graph for us. Then we need to set up a camera. We don't really have something called a camera, but we have view and projection matrices for those who are familiar with GL or D3D. So here you can see we have a function called update projection, and it's using that view info object, looking in this thing called a draw context, which is part of the render graph, and setting the projection matrix of that by calling our math utility library that has a function that will build a perspective matrix for you. And then there's an update camera function that is using the lookAt function from the math library to take an eye, a target, and an up vector and build a view matrix, and then set that into that context. So if we step over to the sample, well, nothing's going to come up yet because we haven't made any content, but this gray area is the area that has been created so far. So now we got to put something on the screen. So the first step, you need to make some materials. Again, we're going to call into the utility function. The first one is going to create just a basic material, and we're going to set it to a green color. We're putting that in this variable red material. Then we're also going to create a checker material. The checker material is actually going to load a shader from a file. The first function, create basic material, actually generated a shader in JavaScript. This one's going to load it from a file. And both of those got created in this pack, and so we're going to, the third part of this thing is we're going to call this function create and bind standard params, which since we created the shaders, we know what parameters they need. If you're familiar with shaders, you specify all these parameters that they need for rendering. Since we know which ones got created, we have this function that will give you a JavaScript object that has ways to access all those parameters in a global way. And so this way we can set the light and the light color for both of those materials with one setting here. Then we're going to create a plane, a ground plane. That's the first line. We're going to create a transform to position that in the world. We're going to parent that transform to our root, and then we're going to add that plane to that transform. We create a cylinder. We create another transform. This time we're going to store it in a global player transform so that we can manipulate it easier later. We're going to parent that to the world, and we're going to add that shape to that transform. And so I go over into step 2. There we go. We have a plane. We have a cylinder. Okay, so now we got to make it do something more interesting. So let's let the user move it. So in this case, we need to track the state of the keyboard. And I think unlike most JavaScript programs, you're usually going to have to, if you're writing a game, you want to know when the key is held down and when it's released, not just when it's pressed. So in this case, we're going to assign some functions to a key up and key down. And you'll see that we actually call into our JavaScript library to do that versus kind of like the DOM way, which we put them on the window or on a div. And that's mostly because we're a plugin. We had to do it that way. If we're ever not a plugin, we'll be able to make it the DOM way. And then you can see the two functions down here. On key down, we're just going to use this global array and set for a particular key whether that key is up or down. If the key is lit up, we'll record that it's been released. Then we're going to add some stuff back in our init function to add a render callback. And that's a JavaScript function that will get called every single frame, and potentially up to 60 hertz or whatever your refresh rate on your monitor is. Most LCD monitors are 60 hertz. And down here you can see the actual function. It gets past this object, which is a render event. Out of that, we're going to pull the elapsed time, and the elapsed time is how much time since the last render event in seconds. So it's useful, and I'll show why. And then we're going to call this function handleMoveKeys. And so here's handleMoveKeys. And so we can see we have direction X and direction Z. That's the direction across our ground plane. And these keys it's checking, the first column it's checking the cursor keys, and the second column is checking ASWD, which are pretty common for a lot of games. And we're setting our direction variables over here. And then we're just going to add those to the player's position. And then before, in the setup, we had the player's transform. We're going to set his translation to where it needs to be to move him around. So if I go over to this step, you should now be able to move him around. He's moving kind of fast. So the next step is we're going to make that frame rate independent. So here we're going to set up a variable for move velocity just to make it easy to tweak. And we're going to say it moves 25 units per second. And then we're going to go into that handleMoveKeys function, and we're going to change that math that we were doing to add to the position to use that move velocity, and before we were just adding the direction. And then we're going to multiply it by the elapsed time, so it'll only move whatever percentage of a second this frame actually handled, and then the rest of the code stayed the same. And so if I go and run step 4, it should now run nice and smooth. And regardless of what frame rate or how the power of the machine that the user has, it should move at the same rate across the field. So the next step is we want to move it relative to the camera. If I go back to the demo, you can see that as I move it across, it's going down the grid. But the grid is kind of at an angle to the camera, and that's not really good for a game. So there's some little math here. I'm not really going to go into the math, but there's this function compute move matrix from view matrix. So before we were computing a view matrix in our update camera function, and if we pass that matrix to this function, it'll return a matrix that we can use to adjust our movement. And so I went into the update camera, and anytime the camera's been updated, I'm going to update this move matrix so I don't have to worry about it anymore. And then I go back into the place that was moving the character, and instead of moving him directly with our direction times our velocity times our elapsed time, I'm going to take that value and multiply it by that move matrix, and it's going to give me two values I can instead use to move the player. So now if I go back and show you that example, you'll see that the player is now moving perpendicular to the camera field, and if I move it in and out, it's moving in and out of the screen. And that's kind of more game-like. So the next step is let's make the camera follow the player. So that's pretty simple. Just take the player's position, stick it in the target, and call update camera. And then we'll put that in a function, and we're going to call it every frame as well in our onRender. So if I go over to that step, now the camera's following the player. But you can see it's kind of stiff. It's not really a good feeling. So let's make the camera a little more smooth. So we'll smooth out the camera. And this is a trick that a lot of video game programmers use. It's not quite frame rate independent, but it's close enough. Basically what we're going to do is instead of using the new place we wanted the camera to be directly, we're going to store that in a variable called newTarget, and then we're just going to call this function lerp, and this says move from the target to the new target, and we're only going to take 3% of that difference and make that the new target. And so if I go run this sample, now the camera will lag behind. So move over here and the camera will catch up. Move over here, the camera will catch up. And that's just a much better feeling than before. So let's add a little bit of action. Let's make the character a little bit more code, and it's a little bit complicated to explain. But in the first part, there's a little variable we're checking if the user's allowed to jump, and I'll go over that in a moment. But here we're checking the space bar. 32 happens to be the key code for the space. If you press the space, set this flag that we're jumping, and set that we can't jump again. That's so we can't keep jumping while we're in the air. And then just set the player's velocity to some value, which we defined elsewhere. And then otherwise, when we come through here, we'll already be jumping. And so we're going to take that velocity, and we're going to add in gravity, and you can see we're multiplying by the elapsed time to make it frame rate independent. And we're going to use that velocity and add it to its position, also multiply by the elapsed time to make that frame rate independent. And then we're checking whether he hit the ground just by checking whether he hit 0. And if he hit 0, then we're going to just force it to 0 and tell him to stop jumping. And then at the bottom, you can see the reason we have this can jump is that we basically don't want it if you hold the spacebar that the player will just keep bouncing. We want to make it that you actually have to press the spacebar to jump again. And so that's why when he's finished jumping, we don't let him jump again until he's released the spacebar. And then finally, in the translate, where we were positioning the player, we added to set the Y position back in. So if I go and do this sample, he should now move around and he should jump. So let's take it to the next step. Let's add a little bit of effect. Here we're going to create a particle emitter. So we have, again, our utility libraries, and we're going to create a particle system. And from that system, we're going to create a particle emitter. We're going to set its state so it's an additive particle. That means the colors add up. We're going to set a little color ramp here. This color ramp says start it at 30% opaque white and go to 0% opaque white or 100% transparent. And then we have all these parameters that set up some particles. So we want to emit 30 particles. We want them to last a half a second, to start at size 5 and scale to size 10 over that time. And then there's some funky math down here at the bottom where if we wanted to set the parameters directly, we could have done just like we did those last parameters. But we want to actually set the velocity of the particles per particle. So I'm doing a little math here, which is just taking a velocity along the ground and rotating it randomly at 360 degrees. So they'll come out at some random place around his feet. And then I actually add a little acceleration so they'll slow as they come away. And then we create an emitter for that, or a one-shot emitter. And then to use it, we just go back into the code where he's jumping. When he lands on the ground, we trigger that effect. So if I go and show you this sample, now when he jumps, there's a poof. Okay, so having, like a checkered plane and a cylinder, okay, programmer art, but you got to add some real art at some point. So the next step is we're going to load a character. And so here, back in our init step, instead of making the cylinder, we deleted that code. We're still going to create a transform for the player, but this time we're going to create a pack, and this is mostly for management reasons. We don't really have to do this, but it keeps things separated. And then we're going to call this function load scene, and we pass in that pack to say everything we loaded create from that pack. And we're going to pass in that player transform to say everything that gets loaded, build under that transform. And here you can see we pass in a path. And then because this is a web API, the whole thing has to be asynchronous because you don't know how long it's going to take to download that. And so when it's finished, we want to tell it to continue in its step 3. And in its step 3 is all the code we used to have below the point of creating the cylinder, plus a few extra lines. These few extra lines are listed here, which is to prepare the pack. That goes through the pack and creates the standard shaders that our utility library will create for you. If you're doing something custom, you might stop there and actually create custom shaders to do something really fancy. And we're going to bind the parameters again from the ones we bound before so that all the shaders that just created for the things that just got loaded will also use the same lighting parameters. And so if I show you that sample, it'll take a little bit longer because I had to load the character, but now we have a character in. Of course, he's not doing much and he's just sliding around. So first step is we actually have to orient the character. That's just a few lines of code. We're going to add a new variable, player direction. We're going to take our move translation, and we're going to compute a target direction, which is stored there. But then instead of just storing it directly, we're going to do our little trick like we did for the camera, and we're just going to take 20% of that target every frame and add it to our current direction. That will smooth them out, because otherwise, since I'm using keys, there are really only 8 directions, right? The 4 directions I can press and the various combinations of those. And so we didn't do that. He just kind of like snap into those directions. And then finally at the bottom, we are actually going to rotate him. And so if I go show you that example, he will now rotate and follow the way he's supposed to go. So that's all fine, but he's sliding. So let's animate him. Right now, animation is really one of the newest parts of the API, and there's still probably some work to do, but we do have something that works. You can see this sample and a sample out in the lobby. Animation is usually told by artists in frames because that's the UI that like Max and Maya and all those other products will usually show. But the API uses seconds. So here we're going to convert the frames they told me that a certain idle started at and store that in a constant and what time it ended at. And then we're making this global variable gAnimTimer to drive this. And then back here when we were setting up, before we load the scene, we're going to create an object, a param object to hold some parameters. And we're going to create a parameter on that, a float parameter called animparam. And we're going to pass that into the loader and say, any animation in this scene drive from this float. And so that's what that does for you. Then, back in our onRender callback, we're going to add a call to a function called HandleAnimation. and we're going to increment that anim timer by the elapsed time. And if it hits the end time, we're going to set it back to the start time. And that mod clamp is just a fancy way of saying anim timer equals idle start time plus the amount you went over end time so that it doesn't lose any of the loop. And then in the end, we set the anim, that anim param that's driving all animation, we set its value to that value. And so if I run this, he will now animate. So that's next step. But of course, he's just going to animate. He's going to slide around. It's not really that useful yet. So let's take it to the next step. Unfortunately, the next step was probably about 40, 50 lines of code. So I'm not really going to show that here. You can download step 12 and step 13 and diff them and see that there isn't really that many changes. But I'll show you step to step. So now he's going to walk around, and when he jumps, and if you leave him idling, he goes through about 4 different idles. They're random. He's got his like little breathing idle, but every once in a while he'll pick something else to do. Since it's random, I could have to stand here, wait forever before he does it, so I'm just going to go back. So the last step is we're going to load a background, and it is just as easy as before, but because it's asynchronous, I'm going to show you another way to do it. And this is, we're going to create something called a loader from our, this is also in our utility library. And what the loader does is it lets you load a bunch of things and then give you a callback when they're all finished loading. Otherwise, you'd have to do that yourself. And so here you see we're going to use the loader to call load scene and load the character. And it's going to, instead of calling init step 3 like it used to, it's just going to call prepare scene. Then we're going to load another scene into another transform, and it's also going to call prepare scene. And at the very beginning, when we created the loader, we tell the loader, when it's finished, call init step 3. So then you can see prepare scene is just like that code that was there before. It's going to prepare the pack. In this case, since that function is going to be called for both scenes, one time it's going to get called, it's going to prepare the character scene. Another time it gets called, it's going to prepare the world scene. It's going to bind the models, and it's going to parent those into our scene. And theoretically, I should get a background with that. So there we go. We have a background. And jump around. And that's our little sample. So one thing I want to make clear is, well, hopefully you see that you can get stuff done pretty quickly. It's pretty fun to develop in this because it's in JavaScript. You just pick refresh. It comes up immediately. And in fact, if you design your code in such a way that you can your on-render callback is being called every frame and it's calling a certain function, you can just take that function and usually paste it into your browser's debugger and actually change the function live as your little app is running. So if you want to update your AI or you want to update some parameters, in fact, yeah, I could go in here now and I could change the particles he emits when he jumps, or I could change his jump height. I usually use Firefox and this in Safari, so I'm not going to go into that. But I do want to show you one other thing, which is a small sample. I feel like I can take it out of here. Which is that we're not really, that was a game, and games are cool, and that's my background is games. But games is not the only thing that O3D is about. And that's kind of why we didn't want to make it too high of a level API, because we really want to make sure that we didn't limit what you could do with it. If we just made an API that was made to make games, then it would be like, well, maybe it's not made to make these other things. And that's kind of also the same reason that Vangelis went over why we went with the JSON format. Maybe you don't want to load models. Maybe you just want to load some lines and widths to do a map, or maybe who knows what your data is. So here's a simple example that we haven't released yet, but we'll put up. Here's a little windowing app I wrote. Took about one evening. And this is actually just one JavaScript app. This is one web page with one O3D area. And all the windows are just implemented in JavaScript, manipulating the render graph and manipulating transforms. And we got little drop shadows and stuff. We've got text in some windows. And it's not really a useful example other than demonstrating that you don't have to make a game. It's really open. The sky's the limit of what you could do with this API. And so, I think I just lost our samples. There we go. That's it. So if you have any questions, please feel free to come up to the mic, and we'll be happy to answer them.
Yeah, quick question. Have you guys been talking with anyone in the X3D group about compatibility?
Not directly, actually. What we did with O3D is we decided. So if you compare X3D to O3D, you'll probably notice that O3D is a much lower level graphics API. We want to create something that you could potentially build a more full-fledged SingGraph API like X3D on top of it, but we really didn't want to constrain sort of the type of applications that are built on it to be sort of just a SingGraph style.
Okay.
So our original intent was to really make a low-level API that will allow you to do different things.
Okay, cheers.
Hi. Are there any plans to import O3D to Android?
Sorry?
Are there plans to port O3D to Android?
To Android. So our mobile story hasn't formed yet. Our first target was really desktops because that's where sort of the capable GPUs, at least for the level of functionality, we want it to be. We know that mobile devices are actually becoming a lot more capable. So there's graphics chips that in the next generation of phones are capable of handling OpenGLES 2.0. So it's definitely something that we're looking forward to looking at afterwards, but it's nothing that we have right now.
The decision of making O3D closer to Direct3D than most game engines, is that a design decision or an implementation type of decision? I mean, are you going to support physics, complex scene graphs in the future? I mean, that's the kind of thing that I don't think it can be done in JavaScript.
Not quite sure I understand the question. Can you say it one more time?
Okay. You said you mentioned that O3D will be closer to Direct3D in complexity than to most game engines, right? Meaning, will you support physics in the future, complex in graphs like oak trees or?
Right. Okay. The question is, O3D is very low level. Are we going to support, I guess, higher level rendering constructs like you'd see in a game for calling or physics? And basically, we released a product last November, native client that lets you run, high performance stuff in the browser. So we're hoping that at some point that will be a solution for those situations.
Thank you.
Hi, when I was watching your demo, I was reminded of a plugin that I think WildTangent had shipped maybe 8 years ago, and they had a 3D plugin for the browser. I think it was IE only. Did a lot of the same things, but I'm very excited because I think they've stopped supporting it, and they certainly shipped a lot of spyware along with it when they had that plugin. So I'm very excited to have a Google kind of open version of this kind of support. So I was wondering if you looked at any kind of plugins that were available in the past and modeled, what your language would be like and how you did the design. What you looked at what was done in the past.
I don't know if we directly looked. I mean, we have this idea that a lot of plugins have been written, but most of them are very high-level apps. They're designed to either run games or to view 3D scenes. Like, you wouldn't do that windowing app in certain, APIs because they're just not, they were meant to do virtual worlds or something. And so I think, well, we're hoping, I guess, maybe that's like the reason this will succeed. And some of those others had trouble because they kind of just decided this is the problem they wanted to solve, and they weren't really generally useful for more things.
How do you handle hardware with differing capabilities, for instance, shader models, etc.? Do you have any sort of automatic fallback capability built into the language or the API?
Well, right now we have, we require shader 2.0, and that's basically all we're shooting for at the moment, because the majority of the market seems to be about 2.0 capable. If your machine doesn't have 2.0, we have a software renderer, should be out soon, and basically, like we said, we're trying to have no cap spits. We don't want you to have to test whether the machine has these features or not have these features.
Right. I mean, what if I wanted to write like a shader model 3.0 program? Can we do that?
You wouldn't be able to do it at this point. And that was a sort of a fine balancing
Sure.
act between, being able to run a wider range of
Right.
machines versus, providing the latest capabilities of the GPUs. As the state of the art sort of progresses, and so the older cards disappear from the market,
Right.
obviously, the API will advance as well. But right now, we're sort of at the shader model 2 level.
It's definitely something you can come discuss on our website. Everything's not set in stone. But the scary thing is like, for example, all the new netbooks are shipping with really low-powered GPUs.
Right.
They'll run this, but they won't run Shader 3.0, and so we don't really want to leave them out of the equation.
Okay, so you're saying there are no cap bits or anything like that? You have to.
At the moment,
mess
there
around.
aren't.
Okay, got it.
Could you comment on the interactive features? What can we get if the user clicks on an object in the scene?
What was that again?
Can you comment on user input or selecting of objects within the scene?
Well, like I said, it's a very low-level API. We have a sample on our website that shows selecting objects. But it's one of those things where, because we have render targets and because we have this whole render graph, we don't really know what you're going to put on the screen. But we have an example that renders a teapot onto a cube. It renders the teapot into a render target, uses that rendered teapot as a texture on the cube. So if you pick, which one do you want to pick? Do you want to pick the cube or do you want to pick the teapot in the cube? And so since that's really up to your app, we basically have for you to implement picking in your app. And we have some samples that show how to do that. And hopefully us or somebody else will write like a higher level one that will just kind of handle all that for you. We have some steps in that direction, but right now we just have the sample that shows how to do it yourself.
My question is about the distribution of the plugin. How big of a download is it? Is it going to ship automatically? And do you have any negotiations going on with Mozilla, some of the others, Opera, to get it automatically shipped with newer versions?
So right now the plugin is a bit less than 2 megs download size. And if you need certain pieces of D3D for Windows, the size grows a little bit. It is a plugin, but we are working on integrating it with Chrome more closely. So in the near future, it will be part of Chrome potentially. And we're talking to other browser vendors to see what their interest level is. For the time being, it's going to continue being a plugin for a bit longer so that you can still get O3D in IE and Firefox and Safari.
Okay, thank you.
Can you comment on how you see this coexisting with the even lower level API that was mentioned in the keynote this morning, the Canvas 3D API being developed at the Kronos Group? Do you see them synergizing in some way?
That's definitely our goal. So when we set out to create this API, our goal was really to create a 3D API for the browser because we thought there was definitely a need for it. And we figured that the fastest way to do that would actually be to implement something and put it out there in order for people to check it out and see how they like the API. At the same time, there's the Mozilla effort, which the goal is very similar, but the approach is different. There's nothing intrinsically that will prevent the two APIs from working together. And there's a lot of cases where you have an API that's a retained mode SIGGRAPH API. Okay. I guess the Mozilla guys are listening to this. So imagine that you have a large scene you want to render, you have a SIGGRAPH, you use a retained mode API to render it. At some point you want to break into to do some immediate mode, to do an effect that you can't easily do with a SIGGRAPH. You can break into that. We understand right now that the sort of the flavor of the API is quite different from GL, but we're hoping that as time goes by, the two sort of will converge at a certain point.
What is the main difference between this thing and there are some existing 3D engines like Paper Vision or Sandy 3D or whatever? How is this better than those?
So the basic difference between this and the Flash plugins that you're referring to is that we're actually making use of the GPU hardware to accelerate 3D graphics. So this is actually, underneath it's running OpenGL and D3D, so it's making full use of the GPU hardware you have as long as you have it. So that's the main difference we see as far as the
performance-wise, how do you see it performing?
So if you look at a lot of the applications that we run, if you open sort of the process monitor for your computer, you're going to see the CPU is mostly idle because really most of the heavy work is taken care of by the GPU. So it really depends. If you have a lot of JavaScript code in your application, there's a lot of logic, you're going to see higher load. But the graphics rendering part is definitely sort of all taken care of, mostly taken care of by the GPU, so the CPU doesn't get bothered. And this is good from a few different perspectives. The one is that it leaves the CPU to, free for other stuff. The second is that from a power perspective, the GPU is more sort of frugal in terms of doing certain things than the CPU. So that's another win for devices where power is important, power consumption.
So is there any example of like MMO developed using this yet, or?
Not yet, but if you want to write one, we're happy to help you.
I'm just wondering if there is something already out there.
The code that you showed looked pretty interesting and not overly daunting, but I'd be real interested in seeing what the JSON file looked like to turn the cylinder into a robot. Is that like 12 megs of picky commas and stuff? Or is
like Vangelis pointed out, we have a sample converter. So some artists made that robot in 3D Studio Max, and then we exported it to Collada. There's a command line utility we provide that converted it to a JSON format, and there's a sample library that deserializes that, or reads that JSON and deserializes. So you can definitely look at it. You just untar the file and you'll see it in there. But it's all sample code. You can change it. I don't think there's anything too mysterious about it.
Well, but just to give you an idea, the JSON file mainly contains the sort of the scene graph content, so the transforms and the shapes. But the actual geometry is stored in the binary buffers. So you won't see in the JSON file in text, you won't see this gigantic arrays of numbers. So you see sort of a fairly terse description of the scene, the transforms that it contains, and then a lot of the other data is referenced in binary buffers somewhere else.
Some of the browsers out there have sort of notoriously bad timer resolution, and that's kind of important for some 3D applications. I'm wondering if you guys have sort of added some of that stuff to your plugin.
I think maybe because we're going off rendering, we haven't noticed those timer issues. I mean, when we first started the project, we were using the timeout function or the interval function, and we weren't getting the performance we wanted. So, I mean, you have things running at 60 hertz in all the browsers. There is the issue of just JavaScript performance in general, which is why we embedded V8. So if you are doing an app that needs the performance, you can switch over to run V8 and make sure you get that performance in every browser.
Very quick question, I'm sorry. Do you plan to support any sort of UI inside the plugin, HTML, something like that?
HTML inside the plugin is probably a ways off because it really requires being integrated. There's no way to get, as a plugin, there's no way to get the bits from the browser into the thing. But you can also just build UIs the same way you build them in Flash or something like that, just by putting stuff up on the screen.
Okay, thanks.
Is it possible to save the status so that when one person finishes, he can go to give it to another person and continue from that stage?
Yes and no. I mean, you'd have to implement that on your own. In the same way that we're like the scenes are loaded in JSON, you can use JavaScript to create JSON, and you could send that to either the HTML5 APIs that let you do local storage, or you can send it through an XML HTTP request to a server. So yeah, you could save state.
All right. Well, thank you very much. If you guys have some time, in the lobby on the sort of the far side, there's 2 or 3 booths of people using O3D. There's a very cool game that's being displayed, another application that shows you how to do some video search using O3D. And in addition to that, we're going to have office hours right after this, so from 4 to 6 on this floor, so on the other side. So if you have more questions, please feel free to come by and talk to us. Thank you.